And now, I'd like to give the floor to a speaker who needs no introduction, Chris Corti. Chris Corti today is going to talk about the enhancement of the strength of high fineness precious metals. He's a very expert technical speaker in the world of gold jewelry. He was always been one of the key speakers at the symposium. He's been always very active at JTF. He's going to be there at the Vicenza Symposium. He's also there as the Santa Fe Symposium. He's had more than 40 years of experience at the World Council, and before setting up his own firm in 2009, he got a PhD in metallurgy at the Surrey University in the UK. And before devoting himself to the precious metals, he has worked in the energy industry in the UK and Switzerland. The subject matter of his presentation today includes a study on high fineness precious metals that are weakened with a low strength, and the objective is that to improve their strength. In the 80s, an alloy was adopted, but it wasn't met with a great success. More recently, different alloys have been developed with the hardened gold alloy as pure as 99.5%. And some of them have now marketing together with microalloys with silver and platinum. His presentation is going to focus on the revision of existing literature. He had tackled the same subject in 2005 and include high pureness alloys. And now the floor over to Dr. Corti. Thank you.
Good morning. I'm going to talk in English. Right, improving the strength of high fineness precious metals. Pure gold, platinum and silver, like all pure metals, are relatively soft. Oh, better, thank you. Are relatively soft with low yield points and hardnesses, and this has several drawbacks in the fabrication of 24-karat gold, pure platinum and pure silver jewellery, limiting design possibilities, as well as making such jewellery heavier and prone to scratching and wear. This problem has traditionally been overcome by alloying to increase hardness and strength, and has led to the use of the carat golds, sterling silver, and 950 platinum, and the lower finenesses of platinum and silver in modern jewellery. However, for gold, especially 24-karat gold of purity greater than 99.0%, is the alloy of choice in the Far East, where it is known as chukam, meaning pure gold, and in the largest market, India, and its subcontinent, 22-karat gold jewellery dominates. These two markets account for around 40% of total jewellery fabrication, and the relative softness of both 22 and 24-karat gold is seen as a weakness. The development of stronger 22 and 24-karat golds has long been desired. For gold, the development of 990 gold, that's a 99% gold, 1% titanium alloy in the late 1980s, hallmarkable as 24-karat, overcame many of the deficiencies of 24-karat gold with good strength and hardness. But it has not met with much commercial success for several reasons. In recent years, however, there have been a number of hardened or improved strength 24-karat gold materials developed with finenesses of 99.5% or higher, some in commercial production, where improved hardness and strength have been achieved by micro-alloying, i.e. the addition of very small amounts typically 0.3% of certain metals, and these are attaining some limited penetration of the market. Microalloyed silver and platinum materials with increased strength and hardness have also been developed and are being commercialised. Until relatively recently, little information was published on such microalloyed precious metals, and that was mainly in patents, and there was little understanding of the metallurgical basis for such materials. The work on microalloyed gold was reviewed by myself at the 1999 Santa Fe Symposium and attempted to explain the theoretical basis for the microalloying of gold. Since then, further information has been published and interest in microalloyed silver and platinum has emerged. Furthermore, interest in hardening high fineness gold, carat golds, has been of interest. This topic was reviewed by the author at the Jewellery Technology Forum in 2005, but more research and information of relevance has since been published. Thus, some 10 years later, it is perhaps appropriate time to update progress and knowledge. This presentation initially focuses on the mechanisms of strengthening metals and then reviews recent developments by conventional alloying of pure precious metals, and then on microalloying of gold, and covers the following aspects. The microalloyed golds that have been developed in terms of their properties in comparison to those of conventional carat golds. The metallurgy, the theoretical basis for hardening, and possible candidate alloying elements which could form the basis of microalloyed 24 karat golds. And published information on the compositions and practical aspects of jewellery manufacture in actual microalloyed 24 karat golds. Progress in hardening of 22 karat and other high karat golds, as well as platinum and silver, is also discussed. The advantages and disadvantages of such materials for jewellery application are considered. We look at the mechanisms of strengthening pure metals by alloying, as well as work hardening by deformation. There are essentially three basic mechanisms of strengthening or hardening pure metals through additions of alloying elements. Solid solubility hardening, dispersion hardening by second phases, and grain refinement. Solid solubility hardening. In hardening by solid solubility, alloying additions dissolve in the pure metal. That is, they are incorporated into the crystal lattice of the pure metal, and this results in the distortion of the crystal lattice, making dislocation slip more difficult. That means it requires more force to deform the metal. The degree of hardening depends on the relative difference in atom size of the pure metal and the alloying metal, as well as the amount that you add. Thus, in carat golds, it is well known that copper is more effective than silver in hardening gold, as its atom is about 13% smaller compared to silver, which is only slightly larger than the gold atom. In dispersion hardening by second phases, when a second phase is dispersed in the metal, it will cause some hardening. Alloys that form eutectics in their microstructure, such as the silver-copper alloys, are good examples here. However, if the second phase is present as very small particles dispersed within the grains or crystals of the parent phase, these impede the movement of dislocations during deformation and cause considerable hardening. Typically, in such alloys, the amount of alloying addition exceeds the limit of solid solubility, and second phases of different composition and or crystal lattice are formed. By careful processing, these can be precipitated out into the parent metal crystal lattice as dispersions of very fine particles. This is known as age hardening or precipitation hardening and is commonly utilised in the carat golds and some platinum alloys. The 990 gold titanium alloy, which I referred to earlier, is hardened by a gold 4 titanium intermetallic phase, for example. It is also worth noting that dispersions of metal oxides, carbides and other ceramic particles can also be used to strengthen metals. An example in precious metals for high temperature application are the oxide dispersion strengthened platinum alloys such as ZGS or ODS platinum, where zirconia or ceria or similar oxides are used. Microalloys, where very small alloying additions result in considerable hardening, also fall into this category of hardening by dispersed phases. Grain refinement, very small additions of certain alloying metals are often used to reduce the crystal or grain size of precious metals and their alloys. This can result in improved ductility, reduced orange peel surface on worked material, and improved strength. The hardening effect of grain size of metal is described by the Hall-Petch equation, in which the yield stress is inversely proportional to the grain size squared. If we look at conventional alloying, here we're talking of adding alloying metals in amounts of at least 0.5% or more. The addition of 1% titanium to pure gold to produce 990 gold has been referred to previously. Other significant improvements to 24 and 22 karat golds have been described using conventional alloying approaches. Dutoit and co-workers at Mintec in South Africa showed that a 995 fineness 24 karat gold containing 0.3% antimony and 0.2% cobalt can be age hardened to a hardness of 131-142 Vickers, depending on aging temperature, as shown in the table. And we can argue whether this is conventional or micro alloying. My feeling is it's probably the latter. Fischer-Bühner, when he was at FEM, has demonstrated the use of circa 2% to 2.5% cobalt additions to effect significant strengthening of 22 karat gold with aged hardnesses of 200 to 260 Vickers, although this involved a relatively high solution annealing temperature of 900 degrees Celsius. And he also showed that a combination of cobalt and antimony, in total 1%, resulted in a hardness of circa 150 Vickers after aging, but using a lower solution temperature of 700 degrees. There is also a patent by Taylor, who patented a 0.4% cobalt containing 22 karat gold, silver, copper alloy, but with a small addition of boron included. And this attains a hardness of 134 after 60% cold work. It is not clear what improvement in properties has been achieved over normal 22 karat gold compositions. We now move to microalloying of gold. I'm going to repeat a lot of what I've said in my earlier review in 2005. But before I start, I just want to say something about the density effect when you're alloying. We must distinguish between the difference between the atom weight and the atom volume in an alloy. The higher atomic numbered metals are heavier and denser. Gold is a heavy metal with a density of 19.32, where silver has a density of only 10.5 and copper a density of only 8.93. Thus, in describing alloy compositions, we must differentiate compositions given in terms of weight percent and atomic percent. Weight percent, the relative weights of alloying metals present, and atomic percent, how many atoms there are of each metal in the alloy. This difference is illustrated with gold-copper alloys. An alloy of 50 atomic percent gold atoms and 50 atomic percent copper atoms, that is 1 gold atom to 1 copper atom, has a weight composition of about 75% gold, 25% copper. And that reflects the difference in the weight of the gold and copper atoms. We look at the theoretical basis for microalloying. In the development of improved strength 24 karat golds, we're looking at total alloying additions of 0.5% or less, typically 0.3%, and even down to only 0.1% in some instances. And this affects a dramatic strengthening of the gold crystal lattice. Such small additions are approaching those values typically used to control grain size by grain refiners, such as cobalt or iridium in carat golds. As gold is a low stacking fault metal, and stacking faults are a type of crystal lattice defect, control of grain size alone or in combination with cold work will not yield significant hardening in pure gold. So such small additions cannot work through grain size control only. Significant solid solution hardening by such small weight additions is only possible if the alloying metal is very light. That is, it has a low density and has a very small atom size compared to gold. If we examine the periodic table, the light metals that might possibly be microalloying additions are in order of density: lithium, potassium, sodium, calcium, magnesium and beryllium, as we can see in the table on the screen. If we assume a maximum alloying level of 0.5% and taking the lightest metal in the table, lithium, then a gold 0.5% lithium alloy, for example, is 12.55 atomic percent lithium, which is within the solid solubility range. This is 1 atom of lithium to every 7 atoms of gold. In comparison, a gold 12.55 atomic percent copper alloy is only 4.4% copper in weight terms, which would increase hardness in the annealed condition to about 40 Vickers and to about 80 in the cold work condition. So maybe a gold lithium alloy could provide some of the necessary property improvement by solid solution hardening. If we look at another light metal, calcium, a gold 0.5 weight percent calcium alloy is only 2.41 atomic percent calcium, which is quite small, only 1 atom in 40, and therefore would not be expected to provide much solid solution strengthening. However, reference to the phase diagram, which is lurking over there somewhere, I think, over here, on the right, reference to the phase diagram shows that there's virtually no solid solution of calcium in gold, and that there is a eutectic comprising 2 phases, gold and an intermetallic compound, gold 5 calcium, which has a high gold content. If this phase is finally dispersed in the microstructure, then we have the basis of a possible alloy system that could provide improved properties through dispersion hardening. We find similar features to the gold-calcium system in the phase diagrams for the gold-potassium system, but less strongly, and in the gold-beryllium, gold-magnesium and gold-sodium phase diagrams, suggesting that they are less favourable for a microalloying approach. Another alloying approach would be to add rare earth metals such as cerium, lanthanum and dysprosium, or gadolinium, as these also tend to have limited solid solubility in gold and to form eutectics and intermetallic compounds with gold. And we'll see a bit of that in a moment in the next slide. Some of the relevant features of their phase diagrams with gold will be shown in the next table. Some rare earths have been omitted from this table just for brevity. From this table, it can be seen that the light rare earths, there we are. From this table, it can be seen that the light rare earths are potentially suitable. The phase diagram for the gold cerium diagram was on the previous slide, down here on the left, and the similarity to the gold-calcium system at the gold-rich end is evident. Also, as the heavy rare earths have solubility at the eutectic temperature in excess of 0.5%, but a very low solubility as the temperature falls, it is possible that they may be amenable to age-hardening treatment with the precipitation of fine particles of the intermetallic compounds on annealing quenched material at low temperatures. And if we just go back again, in the middle there we can see the gold erbium phase diagram, or the gold-rich end of that, showing that the limited solubility as the temperature falls, which suggests that it may be amenable. In the development of 990 gold, Gaffner describes work done by the Degussa company in Germany on other candidate alloy systems, which included the heavy rare earths. The basis for selection was the possibility of second phase precipitation, as the alloy containing a 1% alloying addition in solution was cooled from 800 to 400 degrees Celsius. From this table of probable hardening effectiveness was constructed, and I haven't put it on the slide, but it is in the written paper, which you can get when it's loaded up on the website. The fraction of hardening phase was taken as an indication of the hardening effectiveness. The reason for developing the 990 gold titanium alloy is obvious from this table, as it has the highest fraction. The promise of the rare earths and zirconium was also noted. However, in that work, a 1% alloying addition was being evaluated. If we consider only a 0.5% weight percent addition of rare earth, then from the solubility data at 400 degrees Celsius, we cannot expect much hardening phase to precipitate on annealing solutionized material at 400. Fortunately for us, Degussa carried out some tests on gold rare earth alloys at alloying levels of 1 weight percent and lower. Cast alloys were annealed at 800 for 1 hour. They were also cold rolled up to 95% deformation and subjected to age hardening treatments at a range of temperatures. The table on the slide shows the hardness values attained for gold alloys containing 0.5 of the alloying metal or less. From this work, it can be seen that the annealed hardness is little different from normal pure gold, although cold work material is much harder and in the range of improved 24-karat gold materials. Age hardening heat treatments are not very effective at these low concentrations, with the exception of the 0.5 weight percent gold yttrium alloy, confirming the view expressed earlier that in the consideration of the solubility data, the heavy rare earths suggested little age hardening was possible at these low alloying levels. Whether alloys of gold with the light rare earth metals show good properties was not known at that stage. It is difficult to comment on the results for the gold yttrium alloy, as there is no published gold yttrium phase diagram, but recent work by Ning indicates that it is similar to the heavy rare earths, with some solubility of about 2% of yttrium in gold. So to summarise, the mechanism of hardening by microalloying would appear to be based on some form of dispersion or precipitation hardening by intermetallic phases of high gold content in alloy systems that form eutectics at high gold contents, and where the microalloying addition has little solid solubility in gold. So let's move on and just recap on improved strength 24-karat golds. As I reported in 2005, a number of improved strength 24-karat golds have been developed, some commercially available, and jewellery produced in these materials are in the marketplace, particularly in Japan. All have virtually the same melting point, colour and density as normal pure gold. These are listed on the table on the slide. It is evident from this table that while annealed hardness is usefully higher than for normal commercial pure gold, cold working results in significant hardness increases, and that some materials can be further hardened by low temperature aging heat treatments. Perhaps not surprisingly, the highest hardnesses are achieved in the lower purity golds of about 99.5 to 99.7 fineness. Most can be cast, but the best hardness values are achieved in the wrought condition. often coupled with aging heat treatments. From a practical standpoint, as far as published information tells us, these materials cannot simply be remelted and recycled without loss of strength, as the hardening microalloying additions lose their effect on remelting. As we shall see later, this is due to the oxidation of the microalloying metals on melting. The superior strength of these materials has a beneficial effect in manufacturing jewellery in that certain processes can be done that are difficult with normal 24-karat gold. For example, findings such as lobster claws and some difficult chain designs become feasible. It also allows lighter weight 24-karat gold jewellery to be made with obvious economic benefit. When compared to standard yellow carat golds, it can be seen that the improved strength microalloyed 24-karat golds approach the hardness of 22-karat gold in both annealed and cold work conditions, but are still some way behind those of 18-karat gold. So what are the compositions of these microalloyed golds? The patent literature indicates that the Mitsubishi Materials high-strength pure gold material comprises gold of at least 99.0% purity and 200 to 2,000 parts per million calcium and or beryllium, germanium or boron, whilst a further patent from Mitsubishi indicates just 500 to 2,000 parts per million calcium plus 1 to 50 parts per million of carbon. Calcium appears to be the main hardening addition. The 3O Company patent indicates that the pure gold material contains 99.7% gold plus 50 or more parts per million of gadolinium and optionally 100 to 3,000 parts per million of calcium, aluminium or silicon. In a patent from Tanaka KK in Japan, an alloy for precision casting is claimed containing small amounts of hafnium and the rare earths. There's also other literature on gold bonding wires for electronics application that has relevance. In a paper, Lichtenberger and colleagues doped high purity gold of 5 nines purity with 3 to 30 parts per million of aluminium, calcium, copper, silver and or platinum. They showed that most dopants strengthened the wire during extrusion, and beryllium had the largest effect, but only calcium and beryllium had significant strengthening effects after annealing. This is explained on the basis of atom size difference in the gold lattice. Calcium ion atoms are about 30% larger, and beryllium atoms are about 30% smaller than the gold atom. There will be a tendency for calcium atoms to sit on grain boundaries and pin them. Various patents for improved strength gold bonding wires cite additions of bismuth, the rare earths, calcium with beryllium, europium and niobium, germanium, barium, yttrium and rare earths, or calcium and lead. The choice in this application, these appear to be popular choice in this application. These also appear to be the case for microalloyed golds for jewellery application. The exception in the range of alloys is the hard 24-karat gold alloy developed by Mintec. It was developed to overcome their problems associated with the other microalloy golds that use calcium and or the rare earths, i.e. the loss of strength on remelting due to oxidation of the microalloying metals, and the expense and difficulties in making them. Hard 24-karat gold can be made and processed on conventional equipment and is amenable to remelting without significant loss of strength. The age-hardenable alloy is of 995 fineness and contains 0.2% cobalt and 0.3% antimony. It is based on precipitation hardening by a gold antimony intermetallic AuSb2 with the cobalt retarding recrystallization. The gold antimony phase diagram is a eutectic system at the gold ridge end and shows similar features to those I showed earlier. We look at more recent literature on microalloy 24 karat golds. Further research has been published since my review in 2005. The effect on properties of rare earth additions such as cerium and gadolinium to pure gold and gold alloys has been reported by Ning. He showed that small additions to both pure gold and gold alloys increase the strength significantly and retard recovery and recrystallization, as well as refining the grain size. The strengthening of gold is twofold. One, by solid solution strengthening, but Ning notes that the light alkali earth metals such as beryllium and calcium are more effective. And two, precipitation hardening by intermetallic compounds such as gold 6 rare earth, gold 5 rare earth, or gold 4 rare earth. Which one is formed depends on the atomic weight of the rare earth metal. The light rare earth metals are more effective than the heavier ones as they have lower solid solubility and form the higher gold content in intermetallic phases. In a study of a gold 0.13% germanium alloy, Lai characterised the cause of brittleness that he found. The gold germanium phase diagram is a eutectic system. He found that germanium tends to segregate to grain boundaries as a eutectic phase, which led to the brittleness. In a further study, he reported work on hardening of fine gold by 1% additions of beryllium, and he found that the beryllium addition increased the hardness of gold to about 221 Vickers, but that the alloy was brittle and fractured on attempts to roll it. The as-cast grain size was refined and the microstructure comprised gold dendrites and eutectic phase of gold and the gold 3 beryllium intermetallic. The phase diagram indicates there is almost no solid solubility of beryllium in gold. This work has relevance to microalloying since the use of smaller additions of beryllium are cited in many of the patents. The 2003 patent by Matsuda Sangyo claims the use of 0.12% yttrium and 0.02 to 0.18% calcium for hardening of 24 karat gold. Another patent by the University of Tokyo claims a gold X rare earth alloy where X is selected from aluminium, gallium, indium, germanium, silicon and tin, and the rare earth is a rare earth element. An earlier 2004 patent by Tokariki Honton claims a harder 24 karat gold containing at least 99.5% gold and 5 to 1,000 parts per million of phosphorus, plus 10 to 1,000 parts per million of one of a group including antimony, copper, zinc, iron, cobalt, nickel, gold, silver and gallium. A Chinese patent claims a stronger 99.9% gold microalloy containing calcium and a rare earth element plus a grain refiner, while a 2000 patent by Ogasa claims an age-hardenable 24 karat 99.98% gold microalloy containing gadolinium that reaches a hardness of about 150 Vickers after aging. So I think in summary from all of that, we can say that the more recent literature confirms the use of calcium and rare earth additions as preferred microalloying metals, but other additions are also possible. It confirms age hardening as the major hardening mechanism with the precipitation of high gold content intermetallic phases within the grains. And in the picture, it's a microstructure of the 3O company's pure gold, and we can see there are some precipitates on grain boundaries, but the whole of the internal grains has got a very fine distribution of the intermetallic hardening phase. I'm now going to move on and talk about improved strength 22 karat gold alloys. As noted in my presentation last year here at JTF on the benefit of titanium alloying additions to precious metals, 22 karat golds also tend to be soft due to the limited amount of alloying element that can be added, which is typically silver and copper. Fischer-Bühner developed 22-carat gold alloys containing cobalt or a mixture of cobalt and antimony, as I mentioned earlier, to harden 22-carat golds by conventional alloying. And these have increased hardness by age-hardening treatments, as discussed earlier. Similar work has been reported by Mintec in South Africa. In their 2000 paper, they reported on a new hard 22-carat gold alloy, but gave no details of its composition. It has a colour similar to conventional 22-carat gold, but can attain a peak hardness of 274 Vickers in the cold rolled and aged condition. However, in a later paper in 2003, they describe work on both 99.5% gold and 22-carat gold, that's a gold, copper, silver alloy, in which they study the effects of alloying metals cobalt, germanium, antimony, zirconium and vanadium in hardening them. There they report a maximum hardness of 274 Vickers after cold rolling and aging for a 91.7% gold, 3.84% silver, 1.96% copper and 2.5% cobalt alloy, which suggests that their hard 22-carat gold alloy is hardened by cobalt alone. They show a micrograph of cobalt precipitates growing on the grain boundaries and finer precipitates within the grains, but at that stage they hadn't identified what those finer precipitates were. Work at Pro Gold on hardenable 22-carat gold is described in a 2004 paper which initially examined the effect of cobalt and iridium grain refiner additions on 22-carat gold, silver, copper, zinc alloys. And it was made using a 95% copper, 5% cobalt master alloy. The highest hardness of 230 Vickers was obtained by aging a gold, 3.7% silver, 2% copper, 0.6% zinc and 2% cobalt alloy, yet again demonstrating the effectiveness of cobalt additions. The effect of other alloying additions added via master alloys, such as nickel, gallium and tin, gave gold alloys of good colour that could be easily attain hardness values of 160 to 170 Vickers, with an addition of nickel plus gallium being preferred. And here we can see some results that I'm just going to discuss in the next slide. And I showed this last year, so I'm going to move on quickly and just talk about them. So 22-carat gold alloys I spoke about last year demonstrated that titanium alloy additions act as a grain refiner and allow substantial age hardening. And we saw in that table some results. The commercial use of a 22-carat gold alloy strengthened by titanium, based on this work by the Titan company in India, has allowed jewellery products to be marketed that show a 30% weight reduction compared to conventional 22-carat gold alloys. The figure on the bottom left of the slide shows a hollow bangle in their new alloy. That on the right shows a solid bangle. And my understanding is it's about 0.5 weight% titanium is the alloying addition. And let's just talk about some of the practical aspects of making jewellery in these microalloyed golds. In summary, these are that you can investment cast and fabricate by conventional technologies. You can make some products that are difficult with normal 24-carat gold, as I said earlier, some chain designs, springs, screws, catches and other findings. You can make lightweight, strong chains with good wear properties. Melting generally needs to be done in an inert atmosphere to prevent oxidation of the microalloying metals. Therefore, they cannot be made easily in a small workshop situation by conventional melting in air. As with normal 24-carat gold, soldering must be consistent with local national laws, and in some countries, use of a lower 22-carat solders is allowed, although there may be limits on the amount of solder used. However, another factor is the temperature of soldering, which can lead to a loss of work and age hardening in the vicinity of the soldered joint. Laser welding may offer a better solution there. There are also very low melting point 22 karat gold solders, I might like to remind you, and one solder has a melting point of only 361 degrees Celsius. Polishing should be easier than conventional 24 karat golds as they are harder. And Bernardin, in his paper at the Santa Fe Symposium, noted that castings require procedures similar to those for platinum. Recycling of scrap is generally not viable due to loss of strength on remelting, as we've discussed earlier. The Mintec alloy containing cobalt and antimony is an exception here. However, remelting should allow the gold content to be fully recovered after use. Right, let's just move on quickly to the microalloying of silver. In principle, it will be evident that the same approach for microalloyed gold could be applied to silver. The developer of pure gold also developed a material pure silver, which is a 99.3% silver microalloyed material, and this is being marketed in the USA. It is claimed to be easy to work as it does not require annealing, is very tarnish resistant, casts well, and is harder than sterling silver. The patent covers microalloyed gold, silver, palladium, and platinum materials. In the case of silver, an alloy of at least 80% silver is claimed, containing the rare earth gadolinium in the range of 50 to 1,500 parts per million, with optional further additions of alkaline earth metals, silicon, aluminium, and boron in the range of 50 to 15,000 parts per million in total, with hardness values of 130 Vickers or higher and a Young's modulus of not less than 7,000 kilograms per square millimetre. A further embodiment of the patent claims an alloy of at least 99.45% silver with 50 to 5,000 parts per million of gadolinium, plus further optional additions of the same metals. Hardness values of at least 120 Vickers and a Young's modulus of 7,000 kilograms per millimetre squared are claimed, with hardness rising to at least 140 with 50% cold work. These materials are claimed to be heat treatable. The use of gadolinium is claimed to be the most effective hardening element and results in a high Young's modulus. These small additions do not affect the colour. And lastly, let's talk about microalloying of platinum. Microalloying of platinum should be possible. Of course, oxide dispersion strengthened platinum, as I mentioned earlier, for industrial applications has been on the market for many years. In a patent from Japan, a hard, high-purity platinum alloy containing 10 to 100 parts per million of cerium is claimed that has a good hardness, luster and tarnish resistance, suitable for jewellery manufacture, and is at least 99% purity. Vacuum or inert gas is required during melting to prevent loss of cerium by oxidation. A platinum cerium phase diagram shows characteristics similar to that of the gold cerium system. For cerium contents of 0.03 to 0.3%, hardness values of 60 to 102 were obtained compared to 40 Vickers for pure platinum, and hardnesses of 120 to 136 for 950 fineness platinum alloys. A commercial alloy UHP platinum from Japan appears to be a microalloyed platinum at 999.5% fineness, but little information is available. The Agasa patent that I mentioned earlier also includes platinum materials, and this claims platinum alloys of at least 85% platinum containing gadolinium and the other optional elements listed above for silver, preferably calcium, in the range 50 to 15,000 parts per million in total. Cast hardness values of at least 120 Vickers and Young's modulus of not less than 8,000 kilograms per square millimetre are claimed. With 50% cold work, hardnesses of at least 150 are claimed. Thus, in summary, it is evident that microalloyed platinum alloys are possible, although it is not clear whether they're being commercially produced, and that the rare earths and calcium are preferred microalloying additions, paralleling that of the work on gold. So we can just come to my last slide. I think we can conclude that the metallurgical basis for strengthening and hardening 24-karat gold of at least 990 fineness has been reviewed. This shows that as well as titanium additions, calcium and the rare earths to be the preferred microalloying additions, but other possibilities have been noted. Commercial alloys are available and jewellery is being made in these alloys. The advantages and pitfalls of such alloys for jewellery production have been summarised. The extension of this approach to hardening of 22-karat golds has also been reviewed, where the use of titanium, cobalt and antimony are the preferred additions, mostly as microalloying additions. Hardening of silver and platinum by microalloying has also been reviewed, and their metallurgy parallels that of gold. The silver materials are known to be commercially available in the USA. And lastly, I'd just like to thank many friends and colleagues in the industry for their support in providing information and allowing their data and figures to be used. And I also like to thank the staff of JTF and Lagore for inviting me yet again to present once again and for their kind hospitality. Thank you.
Ringraziamo il dottor Corti.
Thank you very much, Dr. Corti.